So we've already touched on these two men, Ted Happold and Fry Otto. And it was through Ted that I got to work with Fry, along with Ian Liddell, who was the project engineer for the Mannheim project. Ted I knew very well. Fry, I wouldn't say that I knew him that well. He was quite reserved, I guess, in a way. But certainly he had a tremendous effect on all of us who worked with him, particularly Ted's group in Arup and later on at Bureau Happold. And the reason, or one of the reasons why I mentioned them, is because Fry, when he talked, would refer to Darcy Thompson on growth and form. And I guess for those of us who are interested in, if you like, natural forms or organic forms or learning from nature, then Darcy Thompson is always the starting point. So you can see in the slide there a spider's web, which is obviously equivalent to a cable net structure, such as Fry Otto's Munich Olympics Stadium, which was done with Schleich. And of course, the seashell there is analogous to a concrete shell. We could talk for hours, I guess, about the spider's web and the shell. The shell is particularly interesting, I think, because it's corrugated. And if one's going to have a detailed discussion about shell structures, then corrugation is something that one may want to think about. But I don't want to get sidetracked too much talking about that. Maybe we can discuss it later if you've got any questions. So this is the Mannheim project. It was an amazing project to work on. It still seems rather a mad project, really, because it spans 80 meters and it's made from timber like this. So the timber sections there are 50 millimeters square. So it's a very, very slender structure. And we were very much working right on the edge of what was possible. The thing we were most worried about was buckling, and in particular, creep buckling, where the structure slowly deforms with time. Because as you all probably know, a material like timber or indeed concrete doesn't really have a well-defined Young's modulus. And over time, it will deflect. So the structure was originally, the design life was 20 years. And it's now more than 40 years old. And it is deflecting. And Fastenet are advising the client as to remedial measures for the shell. If you want to know how a structure like the Multihaller works, then all you need to do is to get hold of a sieve. This is a woven wire mesh. And so you start with a flat mesh, and then you bend it into a hemispherical shape. And you can do that because you've only got wires going in two directions. If it was fully triangulated, then you wouldn't be able to deform it in that way. Anyway, you could take a sieve such as this, and you could load it with bags of sugar, and then you could do some dimensional analysis on the test results, and use that to predict how a structure like Mannheim would behave. This is the Great Court, which we touched on as well. It's interesting that these projects were separated by about 25 years, and it's now 20 years since the Great Court was finished. This was a lovely project to work on. In particular, I enjoyed working with Filomena Russo, who was the architect at Foster and Partners, so I worked with. The contribution of the client, of the contractor, Wagner Bureau, was very, very important, not just in the building, but also in the design of certain aspects, particularly the joints. The structure is entirely welded, there are no bolts. And that was partly because that's the way that Wagner Bureau liked to work. There are other companies like Miro, for example, who very much prefer to bolt things together. And I guess the debate as to whether you should bolt steel structures together or weld them together is something that will always continue. So what Wagner Bureau did was that they welded what they called ladders. So that's parts of the structure, prefabricated parts of the structure. And then those were brought to site and supported on scaffolding. The whole area was scaffolded. And then those ladders were welded together with full penetration butt welds. The aim was that the connections should be as strong as the members themselves. The members are quite heavy. They're made of steel plate welded together to form the rectangular sections. Two reasons for that. The first reason was that the plates are so thick that in some cases there's almost no air down the middle. They're almost solid. And secondly, Fosters were very keen to use welded plate, because with welded plate, you get a sharp edge to the members. Whereas with rolled hollow sections, you have a slightly rounded corner, which doesn't give you such a nice shadow line. And the nice thing about working with Fosters is that they are very, very interested in all sorts of things at that level of detail. I won't talk too much about this project because there's lots of interesting details, but it's worth noting that because the existing structure of the museum can't carry any horizontal load, the entire roof is sitting on sliding bearings. And that means that the only horizontal thrust can take place into the corners where the edge members can resist the thrust by being in tension. And then we had a long discussion with Fosters about whether we should put tension ties within the roof space, which would have made the roof more efficient. But they were adamant that they didn't want that. And they're probably right, I think. I mean, it's a question of tonnage of steel versus what you see on the inside. Some grid shells in a similar situation do have internal ties. Some of Schleich's grid shells have internal ties, and I think they look quite nice, the internal ties. But this is the sort of discussion that you have. And the nice thing about working with Fosters on this project was that when we had discussions like this, it was an intelligent discussion. There was no sort of stamping of feet or anything like that. So it's a lovely project to work on, and there seemed to be very little stress associated with it, in the sense that there weren't any arguments or anything like that. It was just at the time when computational geometry was just beginning to be used. So I wrote ordinary C++ programs to define the roof. Nowadays, I guess it would have been done with something like Grasshopper. And it did mean that after this project, Foster's set up their own specialist modeling group, so that they now have the expertise to do that sort of thing themselves. So the interesting thing here is that the engineers, so me working with Bureau Happold, defined the geometry, whereas now architects have taken that role over largely. But I would say that in general, for structures like this, it's actually a collaboration between the engineers and the architects. And whether it's the engineer or the architect who does the actual numerical work to define the geometry is, in a sense, neither here nor there, as long as it's done and it's done successfully. Obviously, structural analysis and geometry are very much linked, and sometimes the geometry is very much led by the structural action. Sometimes it's not so clear. Okay, so that's enough about the projects I've worked on. And I'm now going to put my sort of academic hat on, because one of the questions that people ask me is, what should I know about the theory of shell structures, for example? And what I always do is I refer them to this book, Theoretical Elasticity by Green and Zerner. Now, the problem with Green and Zerner, or shell books in general, is that they are quite heavy going, although Green and Zerner is not as bad as some. And that's why I've got the other book there on the left by Dirac, General Theory of Relativity. And the reason I put the two things together is that if you approach shell structures using tensor analysis, which is what they use in Green and Zerner, then you have the mathematical tools necessary to understand the general theory of relativity. And in fact, some of the equations that you have in shell theory are not just similar, but they are identical to the corresponding equations in relativity. And the thing is that relativity theory is basically a geometric theory. And what it does is it links geometry with forces and stresses. And so, as I said, if you're interested in shell structures, then start with Green and Zerner, and you have the added benefit of then being able to understand relativity theory. So what I'm going to do now is just to give you a little bit of understanding of how to get started with this. Green and Zerner is a book about elasticity, but essentially it's a book about continuum mechanics with a special reference to elasticity. Continuum mechanics includes fluid mechanics, elasticity, plasticity, and so on. And the central thing about all these disciplines is the ability to talk about, firstly, whereabouts you are in space, and secondly, about forces which you can resolve into certain directions, and strains and stresses. And the main difference between, say, fluid mechanics and solid mechanics, which includes shell theory, is that in fluid mechanics, you normally have the fluid flowing past your coordinate system, whereas in solid mechanics, if you're sensible, what you do is you have your coordinate system moving with the solid. So that's why I've got this sponge here. And you can see that I've drawn on the sponge a coordinate system. I can move the sponge around, and that's fine. The coordinate system moves with it. from the point of view of the sponge, it takes the coordinate system with it, if you like. And if you had a system of, say, X and Y axes that were fixed in space, they would be, to a large extent, irrelevant. And the same applies to your own body as you move around. You take your coordinate system with you. But of course, also, when the structure is deformed, then the coordinate system is deformed with it. And even if you drew a system of coordinates like this, which consisted of straight lines crossing at right angles, then after you've deformed it, then you no longer have straight lines, and the lines don't cross at right angles. Now, of course, because this sponge is a three-dimensional object, in fact, what you don't have is a series of lines. You have a series of planes. So you could start off, because this sponge is fairly rectangular, you could start off with a whole pile of planes parallel to this direction, cutting it like that, a series of planes cutting it like that, and then a series of planes cutting it like that. So that would be like a Cartesian coordinate system. But then, as I said, once you deform it, then those system of planes become curved surfaces. And so what you have to be able to do is to use those curved surfaces to help you understand what's happening with this material. Of course, what happens is that you don't actually have a real system of coordinates, but you imagine that there was a system of coordinates like that, and you think about them, and then you work out how you think it's behaving. So now I'm going to switch to the computer, to the iPad. So this is a figure from Green and Zerner. What you find with books on shell structures is that elementary books on shell structures have lots of very complicated diagrams. More advanced books like this one, Green and Zerner, have very, very few, very simple diagrams. And the reason for that is that what you do in the more advanced books using tensor analysis is you get the maths to do the work for you. So what we have here is we have a picture showing three planes buried within our material which intersect to define this point here. Okay. And there's a whole pile of planes. On some of them, like this one, the coordinate θ1, this one here, the coordinate θ1 is constant. So you have a whole pile of planes there, which, well, they're not parallel to each other because they're all curved, but they're all part of that family. And then you have the planes θ2 equals constant. Sorry, not planes. There might be planes to begin with, but they're curved surfaces. And then you have these ones, the third one set θ3. Incidentally, I wouldn't have put the 3 at the bottom. I would have put the 3 like that as a superscript, but let's not worry about that too much. Now, so you use these curved surfaces to define where you are by the intersection of a surface from each family. And exactly the same way that with Cartesian coordinates, you have the x equals constant, y equals constant, and z equals constant planes intersecting. But here we've got curved surfaces intersecting. And when the structure is deformed, those planes are also deformed. Now you use coordinates for two main purposes. Three main purposes, if you like. But the first one is just to define where you are. The second one is to define directions in space. And as the body moves, or as the body deforms, those directions change. So at this point here, we define these three directions here, G subscript 1, G subscript 2, and G subscript 3, which lie along the folds, not the folds, the intersection between the planes, so that G1 here lies tangent to this surface and also to this surface at that point. And as you move about, the direction of G1 will change because they're curved surfaces. And the same applies to G2 and G3. So what we've done is we've set up these series of curved surfaces which we can use to define where we are in space. As the body moves and deforms, then those points in space move. And we can also define directions with G1, G2, and G3. Now, one of the most confusing things about tensor analysis is that what you do now is you do something which, on the face of it, seems a bit daft. But what you do is to say that I want to have another set of directions. So we have another direction here, say, and another direction here, and another direction, say somewhere like that. This is all in 3 dimensions. And this one here is described by the vector G1 with a superscript. And G1 with the superscript is perpendicular to this surface. Now with Cartesian coordinates, you don't need to worry about this because the where the x equals constant and y equals constant planes intersect, they do that along a line perpendicular to the z equals constant plane. But here, because these surfaces don't cross at right angles, this direction, which is perpendicular to this surface at this point here, is not the same direction as this one, which is where the surfaces intersect. Now, if you can get your head around that, then everything else is really quite straightforward, because what you do is you use those 2 sets of base vectors, the red ones and the blue ones, for defining things like stress, for example, which is obviously central to everything in shell theory, elasticity, and so on. This may all seem a bit new to you, but of course we're used to curvilinear coordinates, which is what we have here. So for example, on the sphere, you would define where you are in terms of the 2 angles theta and phi, latitude and longitude, or longitude and latitude, whichever. And we're perfectly happy with that. In fact, what's happening here is that we've got 3 systems of surfaces. So there's one surface like this one. This is a plane. It's part of a much larger plane here. psi equals constant is actually a cone. I'm probably not going to be able to draw this very well. There's a cone there. So a point in space is actually defined by the intersection of this plane, this cone, and the sphere of radius r. Now, those system of surfaces do actually cross at right angles, but in general, the surfaces won't cross at right angles. And if you took some sort of problem involving a sphere, maybe you had a squash ball or something like that, and you deformed it, then when you deform it, the surfaces would no longer cross at right angles. Now, this is actually perhaps a bit more relevant to shell theory now, because we've now got a surface. And the surfaces are in some ways simpler than 3D, in some ways more complicated. But you've got your coordinate curves on the surface. So you replace your coordinate surfaces with coordinate curves lying on the surface of your shell structure. And this equation here is what you use if you wanted to calculate the distance ds between 2 points. So between these 2 points, the coordinates, which are sometimes called x with superscripts or theta with superscripts, as they change, you move, and this equation gives you the distance between those points. Those of you who do lots of stuff with Rhino and computer programs like that will be used to using u and v as your surface parameters when you're describing a surface. But it's much better to actually use things with superscripts, even though it's confusing to begin with. These things, the g's, are what's called the components of the metric tensor. And those enable you to do this calculation of distance. This formula, even though it doesn't look like it, is actually very much the same as the cosine rule that you're used to using instead of Pythagoras. So you know, with a right angle triangle, you use Pythagoras' theorem. With a triangle that's not right angle, you use the cosine rule. And this equation here is effectively the cosine rule. Now, the nice thing about this is that not only does this allow you to calculate the distance between these 2 points, this point and this point, it also allows you to talk about strain, because what strain is a change in the distance between 2 points. So if you know how all the distances change between different points on the surface, then you know everything there is to know about the deformation of the surface. So if you understand this stuff about these g's, then you can immediately have a very simple explanation of what strain is. It's much more difficult trying to describe strain in, say, Cartesian coordinates, because you have the fixed coordinates, if you like, and then you have your material moving past the coordinates. And it's an incredibly messy way of looking at it. Whereas looking at it this way, with your coordinates being dragged with the material, everything is straightforward, except for the fact that you've got these rather annoying subscripts and superscripts. Here, in this bit here, there's a sigma I equals 1 to 2, j equals 1 to 2. And that's used all the time in tensor analysis. It's the Einstein summation convention. Okay, so I won't talk about this in any detail, except to say that probably some of it is familiar to you or to some of you. So, for example, these are the equations of equilibrium of a two-dimensional continuum with no load. So you've just got stresses within the material, but you haven't got any gravity or anything in it. Now, this sort of thing, well, I learned this when I was a student, and I used to teach it when I was at Bath. But it's quite possible that some of you, particularly in the UK, will have managed to complete your engineering education without ever seeing these equations. I don't know. We could have a long discussion about how much of this stuff you should have, if any, in an engineering course. So sigma x, you're probably familiar with. Tor xy and tor yx, which are equal, that's this equation here, through complementary shear stresses. And basically, this equation tells us how the stresses can vary within a material in order to maintain equilibrium. So this is in Cartesian coordinates. This here is in curvilinear coordinates. And you can see immediately that the equation is much shorter because it uses the summation convention, which we just mentioned. It also applies in 3 dimensions as well as in 2 dimensions. And actually, it also applies in 4 dimensions of relativity. And in relativity theory, shows that that equation, the equilibrium equation, is actually a geometrical property of space-time. But we're getting a bit away from ourselves. It's also nice to be able to write equations without a coordinate system, because in real life, you don't have a coordinate system. So if you say, well, in order to write down equations, I have to imagine a coordinate system, that seems a bit sort of, a bit dumb, really, a bit inelegant. And so this equation, these here, the sigma equals sigma t, means that the stress tensor is the same as its transpose, and that's the complementary shear strain. Shear stresses are equal. So all these equations here are saying the same thing. And then those of you who know a little bit about elasticity will know that in 2 dimensions, you can satisfy those equations by introducing phi, which is the area stress function. And again, you can write that down in different ways. The stress function, area stress function, is used quite a lot in shell theory, where what you do is you use this 2-dimensional analysis in plan. So you look down on your shell structure, and what you see is a 2-dimensional structure in equilibrium in a horizontal direction. And all these equations remain unchanged. Well, the equilibrium equations remain unchanged. The other ones do change. And then what you do is to say, well, actually, I've got a curved shell structure, and you then use the area stress function together with the height of the shell, the variation in the height of the shell, to give you the equilibrium equation in the z direction. Anyway, sticking with 2 dimensions, we then have these relationships here between the displacements u and v, or in this case here, u1 and u2, and the strains. This is the direct strain, tensile strain, and this is the shear strain. And these three equations are summarized by this one equation in tensor analysis. What happens here is the half is quite interesting because this definition gives the same result as this one and this one, because you basically get half of something plus the same thing. So you lose the half. What happens here is that there's actually not so much a mistake, but it's a bit of a mistake. There really ought to be a half in here, but there isn't. I don't know whether you will be aware of more circles for strain. You're probably aware of more circles for stress, but there's also more circle for strain. And in more circle for strain, you have to put a half in front of the shear strain. And the reason for that is because whoever decided to define shear strain in this way should have left the half out. It's rather annoying, really, because it means that both the shear modulus in elasticity and also the viscosity in fluid mechanics have got a rather annoying lack of a half there. Anyway, not to worry about that. We then have constitutive equations which relate strains to stresses. And again, they become simpler here if you use the tensor notation. And this equation, the tensor notation here, applies in both 3 dimensions and 2 dimensions. Whereas if you use the Cartesian notation, it gets very messy in 3 dimensions because you've got 6 components of 6 components of stress and 6 components of strain. And then you can also write them here if you want to be a bit more elegant without using any coordinate system. So what we have here is things like stress here is a tensor, which is an extension of a vector, if you like. So you start off with scalars, and then you have vectors, and then you have higher order tensors. So stress is a second order tensor. Vectors like force are first order tensors, and scalars like density are 0th order tensors. Anyway, so you have these compatibility equations. You have constitutive equations, compatibility equations, and when you combine them, from the compatibility equations, you get this. Then you can put this into there, and you finally end up with one differential equation for the stress function, which you can write in this notation, or this notation, or this notation. The nice thing about this equation, the biharmonic equation, is that it's the same equation that you get in plate bending. So you can get quite a lot of understanding about stresses in 2D from plate bending. And this picture here is just an example of the stresses that you get around a circular hole, where essentially what you have to do is to solve this equation, biharmonic equation, in polar coordinates. And you probably, if you want to do that, you probably do best to look at Timoshenko theory of elasticity, which is the classic book on, if you like, conventional non-tensor elasticity theory. Right, so that is the end of my talk.